Hello, everybody, and welcome to tonight's webinar. You are currently in listen-only mode, like the voice in your head just said. What that means is you can hear everything that's going on, but you will not be able to chat with the presenter or myself. And that's done so that we can concentrate and everybody else can concentrate on what's going on. Mr. Deal will be presenting today on explorations with complex numbers. On the side there, you've got a little pane that lets you control things like chat and questions. Should you have any chats or questions, feel free to chime in. I'm Ismail Zamora. I will be your facilitator today. I'll be answering those questions. If a question is something that we should uh, pause John and ask him, we will go ahead and do that. If not, I will try to handle them as best I can. If you've got any technical issues, please feel free to ask me. If you would like to chat, that's also available to you. I'll be answering the chats as well if you would like to post a question on that. Also, Mr. Deal today will be using a handout. The handout will be sent to your email, so all the registered participants will be getting a copy of today's presentation via email, but it's not currently available. We will send you that out as soon as we are done with the webinar. John Deal is a retired math department chair from Hinsdale Central High School in Hinsdale, Illinois. He's also the current president of CTAC, that's Casio Teachers Advisory Council. He's the president of that organization. And he's going to be presenting on exploring with complex numbers, like I mentioned. His screen is the one you will be looking at. He's also got the emulator screen up. If you want to follow along on your emulator or calculator, if you have a handheld, feel free. If you would like to just watch and see how this is done, you could also do that. This webinar will eventually be on Casio's YouTube channel, which houses all of our webinars. If you look us up on YouTube, you can find us there. But that's all I've got. Mr. Deal, are you ready?
Yes, sir. Thank you very much, Ish, for that
All right.
introduction. And good evening, everyone, and welcome. And thanks to you for joining us on tonight's webinar. We have some explorations with complex numbers. I think the webinar is best described as broken into two parts. Part number one that I'm calling initial explorations. We'll look at some traditional topics. I think topics that would generally be in an algebra, advanced algebra, college algebra, pre-calculus course, and take a look at some arithmetic and some polynomial equations and other things that involve complex numbers, especially how they're handled by our Casio Prism. The other half of the webinar, I think I would describe that more as a bit beyond the curriculum, hopefully of interest to teachers, where we look at some non-traditional topics and perhaps a few surprises about domains and ranges and other things where we look at extending functions that we generally think of as using only real numbers and look at what happens with some non-real complex numbers. As Ish said, please type in any questions to him, and I'll pause every now and then and make sure we get all your questions answered. But for now, we're going to start with a little demonstration of some of the basics. And I'm going to clarify that in case you happen to be new on your Casio Prism, we push the menu button and we go here to menu choice 1, run matrix, and I think of that as essentially your scientific calculator menu where you do your basic computations. And we can push either the 1 key or the execute key to go here. Now, probably the most important thing to mention as we begin some explorations with complex numbers would be in the setup, there are some choices that will change what happens. Please notice setup is here in row 2. It's the second function of the menu key. So let's literally go there to setup. Scroll down a little bit to this choice, complex mode. And we see that there are actually 3 choices. We're going to call these tabs that appear above our F1, F2, F3 keys in this case. So if I push F1, now complex mode is read as real. Essentially, that means we've disabled complex number results. Then we have traditional rectangular a plus bi, and then what I think of as a polar mode, telling us the radius and the angle if this number were plotted in the complex number plane. More about that in a little bit. But and also while I'm here, I'm going to point out right above here is an angle choice, and when we do speak about those angles, we can actually be in either radians or degrees, again, by using these tabs to make that choice. So let's leave the setup in real numbers for a moment, press exit, and type in a typical type of question, the square root of -4. And when we do that, we see this non-real error. I don't know if we should really call it an error, but it's simply saying, given the choices you've made, which is to disable the complex numbers, then your result is not real. Here's a little helpful hint also. Up on the top of the calculator, what we kind of think of as the status bar, there's actually a little clue there that this calculator is right now only displaying real. And I find that convenient to have that. If we go into the setup now, and I think I have to restore my regular mouse to do this, and we change that to a plus bi, numbers are enabled, press exit. Notice again in the status bar, it actually does tell us that, a plus bi. And when we execute this command again, now we get the result we would expect if we were allowing the complex numbers. So 2i is displayed as the square root of -4. Now, another interesting result, and even a little bit more involved, would be to talk about a cube root of a negative number. I will illustrate. I'm going to go back to setup for a minute for reasons that will be more clear as we do this example. I'm going to set it back to real mode. And then I'm going to type in a question, shift root, cube root of -8. And we execute. And we get the result I think most of us would expect. Cube root of -8, -2. Even though we're in real mode, it's no problem because that's a real result. And -2 is displayed. But let's imitate the process again. Go back to setup. And again, enable complex numbers. I'll just highlight this and press execute again. Well, that's very interesting. We just got a different result. One that you might not expect right off the bat for what is the cube root of -8. But perhaps as a bit of explanation, it's probably not correct to say what is the cube root of -8. There are, in fact, 3 cube roots of -8. Technically, there's also 2 square roots of -4, but we have an alternate symbol for the other one where we actually put an opposite sign outside the radical. And I don't think we have such a clear convention on what we would do on this cube root question. So what in the world is happening here? Well, it's related to what I was talking about actually, of if you plot complex numbers in a complex number plane, and each one has a certain angle. So I'm going to describe this as the principal value square root, the principal value cube root. And think principal value as the one with the smallest angle. And in fact, if you make that third choice in setup, if you choose to actually display the R and theta mode, if I repeat the question again, we see that that in fact has an angle of 60. And negative 2 has an angle of 180. This angle is actually smaller. Thus, it is returned by the calculator as the principal cube root of negative 8. I hope I just reinforced it's pretty important to pay attention to what your setup is there, as using real mode or A plus BI mode uh, showed a different result for that question, cube root of negative 8. And in fact, if you have your angle set to radians, you would yet get another result of using pi over 3 rather than the 60. So all of a sudden we've just realized we have 4 different results that are returned for the command cube root of negative 8 depending on your complex mode setting and your angle setting. We're going to return to this concept of the r and theta in just a little bit after we do a few more examples here in this menu. I'll show you something else in the graph menu. But let's let this particular example go for the moment and return to the more common A plus BI choice in setup. Probably the second most important thing to know when working with some complex numbers and just in computation mode here is how to get the number itself. So it's important to look on our keyboard again for a moment, that here on the 0 key in yellow we have I, lowercase I. That is indeed the number I. So it is a shift 0 that obtains the number I. There is an uppercase I here, but that is just like any other letter of the alphabet and treated essentially as an algebraic variable. So always this is where we obtain I for computation purposes. All right, so let's do a problem that I taught for many years by pencil and paper technique, and there was actually a lot to do by pencil and paper, which would be divide one complex number by another. I'm going to use the fraction key to make this look as best as possible. Reminder, now I'm going to put 2i, so it's shift 0. I'll use the right arrow to move to the denominator and put another value, 3, another expression rather, 3 minus 4i. So again, taught this for many years. Have to prompt the idea, multiply top and bottom by the conjugate, multiply 2 binomials in the numerator, multiply 2 binomials in the denominator, simplify both expressions, simplify further if the values allow it. Well, all I'm going to say is that's easier. And we now have even some of our scientific calculators can very easily do this type of complex number arithmetic. And notice it, rather than putting a single expression with a denominator of 25, it even went to an A plus BI form there for the result. And an exact fraction display, which I like. As another example that I remember teaching would be, what about the square root of a non-real complex number? Something like this. What's the square root of 5 plus 12i? Well, again, I remember teaching this by pencil and paper, essentially setting the square root of 5 plus 12i equal to an unknown complex number, a plus bi, square both sides, equate the real coefficients and the imaginary coefficients, and getting a system in the two variables a and b and solving that system. Let's just say it was a lot of algebra. Here, execute, presto, we've got it. Square root of 5 plus 12i is 3 plus 2i. And of course you can do fun things like this, talk about hey, just verify that, make sure everything seems to be good in this world of complex numbers. If we took 3 plus 2i and squared it, yes, indeed, we get 5 plus 12i, and things are looking good. So that's just a few examples where we look at a square root of a negative number, a cube root of a negative number, a quotient of some non-real complex numbers, square root of a non-real complex number, just to get the idea of how the complex numbers behave on this particular calculator. Anything come up so far, Ish?
Nope, so far so good. All the questions have been just basics. Where do I find some of the keys? But you are doing very well, thank you.
All right. Appreciate that. Uh, Next thing I want to suggest, as far as where do the complex numbers appear probably within our curriculum, would be here in solutions, certainly for quadratic and maybe in some of the higher courses, other polynomial equations. So I'm going to go to row 2. I'm going to push menu, and I'm going to go to this choice, equation. Again, I can literally just push the A button, but I'm going to move here and highlight it to emphasize for those that are working along with where are we at here. We're in the third row. And just the way this is set up, each of these menus has a character, but once we got 1 through 9, rather than going into double digit numbers, they change to a letter. So this is actually choice A, equation solver. So if we push the A, which is the X, and you don't have to push alpha in this case, or we just push execute. Either way, we've opened up the equation menu. Now within the equation menu, we have various things we can do. Just in case you haven't seen this, this is solving simultaneous linear systems. That's not where we're going to go now, but I just thought I'd mention what that was. F3 is more of a general solver, but for polynomials, well, that's fairly evident. Let's try and literally use this polynomial solver. So again, with these prompts, F1, F2, F3, literally we're going to push the F2 key and open up the submenu for polynomials. All right, first choice is what degree do you want to work in? If we're going to work with a quadratic equation, then of course we would push 2. Now this particular screen is helpful. It helps you realize that this assumes that one side of your equation is 0. So your quadratic equation, you may be rearranging some terms to make sure that is so, and that the coefficients literally go in the order A as the coefficient of the x squared, b, and c. So this just removes any doubt about, I hope, what these values would be. So if we were going to solve something like x squared plus 4x plus 6 equals 0, we would put a 1x squared, hit execute, plus 4x, execute, plus 6, execute. We now have the 3 coefficients entered, and we would get our result. Notice there's a tab above F1 that says solve. That's the one we want. F1, presto. Think of all those years that we, again, used a pencil and paper approach to the quadratic formula. Now we get them this easily. And I find it very interesting that in this display that I'm looking at on the upper part of my calculator screen, I have decimal estimates, but actually in the lower right, there's the exact radical form for that root. And if I push the down arrow to scroll down one, I get the, I mean, I guess if we knew one, we're probably pretty sure what the other one is, as they should be conjugate pairs, but I am simply acknowledging that both of those are displayed as exact solutions to that equation. Just to clarify, in case you're actually using this and you get somewhat of a surprising result, that whole setup thing um, is valid here too. I have to push exit and get out of this solution screen. Now in setup, it's not quite the same setup as before because remember we went to a new menu equation, but there still are some of the choices, including the complex mode. And again, you could essentially disable that. It's not very interesting in this case then, but it says the right thing. No real roots. So again, if at some point half the students are saying I see an answer and half the students are saying I don't see an answer, that setup is the thing to check between what we have. Let's go back, put it back to enable A plus BI. Let's try a cubic equation. Notice right here I'm still at ax squared. In row 3, the exit key takes us back one screen. Perfect. It's right where we wanted to be. Back to the question of, we're in polynomial solver, what degree would you like to use? We'd like to go degree 3 this time. So we push F2. And let's suppose we were solving x cubed, or 1x cubed, minus x squared. So negative 1 is the second coefficient. 0x plus 2. I apologize. I hit something there that was unintentional. I'm going to have to go back here and say that I said I believe was 2. I'm pretty sure that's the equation I said. Sorry. Had a little trouble putting my C and D in. X cubed minus x squared plus 2 is equal to 0. Press solve. Again, we see all three solutions to that equation. The real solution, negative 1, and the other solutions, 1 plus I, 1 minus I. And of course, those are a conjugate pair again. I have recall again of teaching this, and the technique used to be first search for a rational root. Use the rational root theorem to help compile a list of potential rational roots. Do synthetic division until you found one. And after you did the division, solve the remaining quadratic equation by quadratic formula. So having done that technique for many years, I kind of have an admiration for this technique on the calculator of how it obtains those solutions in exact form just that easily. And to try to make one connection, if I go back and remember, we talked a little bit about the cube roots of negative 8. Let's look at that as an alternate way we might see it. How about if we think, well, if we want the cube root of negative 8, it's like x cubed equals negative 8, or x cubed plus 8 equals 0. So let's make the coefficient of x squared 0, and let's change the constant to 8. So again, my intent here is to say we are now solving x cubed plus 8 equals 0. Press F1 to solve. There we see the negative 2, and in decimal estimate form, the other two cube roots of negative 8. Once again, scroll down, highlight it. It's in exact form. And I believe that was the one that we saw on the home screen earlier for reasons I explained at that time, being the principal value. and the third. So I kind of like this as a reinforcement of why I think it's correct to say there are three cube roots. And in fact, here's a kind of a nice way to find all of them at the same time. We're going to look at that yet a third way in just a moment here. But again, I'm going to pause again for a moment and see if there's any comments, thoughts, or questions about using this polynomial solver.
Actually, there was. There was Bob from Des Moines pointed out that when you made your little mistake there and you forgot to put the 0 or the 2 in, you got an x2, which I explained to him was the multiplicity of one of the roots. So you ended up with two roots, a 1 and a 0, and 0 had a multiplicity of 2, and it actually showed up with multiplicity, which was a kind
Interesting.
of neat
I'd actually
feature.
like to revisit that if you remember all of
Sure.
the coefficients.
-1 for B,
Okay.
and then everything else is a 0. And
Okay.
then go ahead
Oh,
and
I see.
solve that one.
So
Yeah.
we have x cubed minus x squared,
Yep.
which the traditional way would be factoring it out. And here in the pink or magenta, it's actually acknowledging what you said,
Yeah.
that that's a double root.
Yep.
I had not caught that in the past. So
No, me
thank
neither.
you, sir.
That was a good thing by Bob there in Des Moines who picked that up pretty quickly. I was wondering myself, what was that? But that's pretty cool.
Well, very good. Thanks. And as a happy graduate of Drake University, I spent some happy years in Des Moines myself. So there we go.
Thank you.
Very good question. Thanks a lot for that observation. Anything else to tie up here?
No, nope. So far, so good.
All right. Well, I'd like to go to a slightly different technique. I'd like to stick to the world of roots for a minute. In fact, start with cube roots still, but I'd like to reinforce something I mentioned earlier about the complex number plane and plotting numbers in the complex number plane and having a look at this. And so I am going to go back to menu and I'm actually going to go to graphing. Again, you can just push 5, but I like to, when demonstrating, highlight, make it perfectly clear what we're doing. We're making menu choice 5 where we do graphs. And I think it would be an incredible coincidence if anybody's y equals screen looks exactly like mine at the moment. And I'm going to clarify that. This would be the typical, that we're graphing y equals f of x functions, but I'm not going to do that. I am actually going to use something called a polar graph. And again, because some folks may be new with this calculator, you can graph any types here. You don't go to a different place for polar or parametric or vertical lines or x equals some function of y. I think this happens to be a great opportunity here to mix and match the types of functions and relations you want to plot. But as a point of instruction, to change, you go to this tab that says type right above F3. And I want to go to the polar mode, which is R equal. And you can see that change that automatically. I'm just going to put R equals 2 in here, and then I'll clarify what's this graphing method. Again, just in case you're used to slightly different models, when you enter something for graphing purposes, be sure you push the execute key. There's two clues that all is good. The 2 turned blue and the cursor jumped down a row. Now, if you think a little bit about polar graphing, when we say R is 2, that simply should be a nice circle. Two cautions about polar graphing. It's kind of important to tell it what you want to use for theta. And when you're going to do that, it's kind of important to notice what uh, is your angle set at degrees or radians. I'll reinforce the status bar. I happen to be in degrees, and I think that would be best for what I'm going to illustrate right now. But just something to check. And the second thing is if you go, notice here we haven't set any windows for graphing purposes yet, but if you go to a viewing window, I'm sorry, I hit an F1 and I did not mean to. Shift F3 goes to viewing window, and here's where you have a theta min and a theta max, and what looks like pitch, but I believe it's actually an abbreviation for point change, which is, in other words, what increment would you like to do? How many points do you want to plot? One would be more than enough. That will actually do 361 computations and plot each one of those points. So that's more than enough. Also, as long as we're here. I did preset this. Remember, I'm expecting a circle of radius 2. So I made the y's go from -3 to 3. I made the x's go from -6 to 6, although not perfect. It's very, very close to a 2-to-1 ratio in this window. And if you've done some of this before with conics or any other type of graphing, I think you know what I'm getting at. Your circle will be a bit distorted if you don't pay attention to your aspect ratio. So that should be a good choice. And if we say R is 2 with a window we're happy with, and we press F6 to draw, we get, as expected, a circle of radius 2. Now, what does that have to do with complex numbers? Well, not too much yet, but I wanted to clarify what we were putting in the screen. If I could get you to take a look at the PowerPoint over here on the right for a minute, we have one of my favorite mathematicians, Abram Demoivre. Although Ish and I grew up near Chicago, we might call him Demoivre there, but I believe he was French, and the correct pronunciation would be Demoivre. So here is really how this polar idea makes even more sense. You can express an a plus bi number like so. X equals r times cosine theta plus I sine theta. And so, for example, to go back to when r was 2 and theta was 60 degrees, now we start to see where, oh, we had 2 times radical 3 over 2 plus I times a half. You know, that's where things like the radical 3 plus I and so on would come from, is this form. And so when we put that calculator in r theta mode, that's actually what it's telling us. What is the r and the theta if the number is expressed this way? Well, this rather famous theorem says if you take the nth root of the number, you take the nth root of the radius, but you divide the angle by n. Well, it doesn't mean a lot if we think of the number 8 as r is 8 and the angle is 0, although that's correct. But check out what happens if we apply the theorem. We get the cube root of 8, which is 2, and 0 divided by 3 is still 0, and this theorem actually verifies one of the cube roots of 8 is 2. Okay, but what's going on? Well, what's more interesting is, well, you know what? 8 could also be thought of as, say, 360 degrees. And if we divide that by 3, we would get 120 here. And if we use 720 degrees, we would get 240. And so my point is that the cube roots of 8 are located in 3 positions, and the angles are 0, 120, and 240. And in fact, they're 120 degrees apart, which should always happen in a cube root situation. So what am I going to do in my grapher? I'm simply going to go back to the window and say, you know what, I don't want you to plot all those points. I don't want you to plot 361 points. I, in fact, want you to use point change of 120. In other words, please only plot the points at 0, 120, and 240. And actually, it will use 360, which will nicely close off the picture. Let's see what we get now in the picture. We get a triangle. And if we trace on the triangle, we start here. So one of the cube roots of 8 is 2. If you look closely, you'll see that 2, 0 is actually shown as the coordinate to that point when I trace. Let me try something. There, I can push execute and actually mark that point. Notice on the bottom of the screen, we alternately get the polar form. So we have both. R is 2, theta is 0. If I push the right arrow, we now have another cube root of 8. -1, comma 1.732. Well, it is comma because it's essentially polar graphing mode, but what it really means is that another cube root is -1 plus square root 3i. And again, on the bottom, in polar mode, the angle is 120. If I go to the right again, I get the third, -1 minus square root 3i. What we really have then is this equilateral triangle that connects those cube roots together. And again, reinforcing that the angle is 240. This vertical line reinforces that these two are a complex conjugate pair. They have the same real part and their imaginary parts are opposites. So a nice way to, I think, illustrate these roots. Let me reinforce the math behind what just happened. 8 is 8 times cosine 360, cube root of 8, we use the 120. Cosine of 120 is a half. Sine of 120 is square root 3 over 2. And we have this value. Actually, there's a math error in there, isn't there? Should be a -1/2 and a -1. Apologize for that. At least I caught it and I'm saying it correctly. But there's a little sign error right here. Now, let's go back to the cube root of -8 because that's going to be slightly different. We have to agree that we kind of understand the real cube root of -8. One of the cube roots of -8 is at -2. So this picture, of course, is not correct for that. So how could we alter what we're doing? Well, the easiest way, I think, is to think of -2 is located at an angle of 180. Start there, plot that one first. Now you have to go all the way around a full 360 degrees, so change this to 180 plus 360, which is 540. And 120 should again still be correct. Let's look at our drawing now. Here are the cube roots of -8. -2 is the one we probably knew. And then here is the 1 minus the square root of 3i. And here is 1 plus the square root of 3i. And we have another equilateral triangle, but in a slightly different location. Just because I'm having so much fun, as one more illustration, suppose I challenge the students to tell me all fifth roots of 32. I want to know all the fifth roots of 32. Now, honestly, out of convenience, I picked another example where one of them is at 2. That'll speed things along a little bit. I can still use r equals 2. One of them is located again at angle 0 to 360. But now for fifth roots, I need to rethink they should occur every 72 degrees. 360 divided by 5. Let's have a look. There they are. All of the fifth roots of 32, the 2 we would expect, and all these other non-real complex numbers. Again, there's now a pair of conjugates right there. There's a pair of conjugates right there. And I guess I want to conclude this piece by saying you should expect that these root questions always make regular polygons in this complex number plane. So we saw a couple of examples of equilateral triangles. Now we've got a regular pentagon, and for different roots, you're going to have different values and different size polygons, but they should all be regular polygons. I really like this theorem. I think there's a lot here. It's algebra, it's trigonometry, it's geometry, and there's a lot going on, and I really enjoy the visual. Can I just make sure I've really clarified, though, if you have a more elaborate, no, I shouldn't say more elaborate, but not everything uses r equals 2, of course. If we go back and we're talking about the cube roots of 27, you have to think, well, they're going to be at a distance of 3, and you'll have to change to r equals 3. So this has to be chosen depending on what's the real value, and therefore the radius, if you will, of all of these values. And then you can, I guess I said another cube root problem. If it were positive 27, we'd be good. With the 0 to 360, 120. And so notice a bigger triangle with the correct solutions now are showing me 3 and these complex numbers over here. De Moivre's theorem, one of my favorites, and again, I think there's so many connections there between algebra, geometry, trigonometry, polynomial equations, roots, lots happening. And this is a fun way, I think, to visualize what's happening. Let me pause there for a minute and see where we're at with thoughts, questions.
Just one comment. Michelle in Florida said it finally makes sense to her that she's been teaching De Moivre's theorem or De Moivre for a number of years, and it didn't really click. And finally, with the graphic, like you said, it absolutely clicks and makes great sense, and she's going to be using it. So Michelle's picking something up.
Well, good. Glad to hear that. And I know that was actually a lot to go through in a short webinar, but again, if I'm going to call this explorations with complex numbers, that's one of my favorites. Thank you.
Yep.
All right. Well, as I promised in the beginning, part of the webinar would be to go a little bit beyond the curriculum. And I'm kind of glancing at the clock too, to be honest, and I may not be able to do all of what is on the handout you'll receive, but we'll do whatever we can to take a look at in the time allowed. Because I think there's some good math, but I think there's some fun and surprising results that we might see as well. So I am going to go to menu, return back to the good old Run Matrix home screen, and I'm just going to clean things up. And you do that by using the delete key. Delete them all is okay. Safety check, are you sure you really want to do that? Yeah, I'm fine with that. All right, so some results. This happened to me by accident once, to tell the truth, and it went places from there. Can you take a logarithm of a negative number? I think in class we probably say, well, no, we don't take logarithms of negative numbers. The domain of the logarithm function is only positives greater than 0. But this accident led to some interesting explorations. Check it out with me. The natural logarithm of negative 1 is not an error message. Apparently it does exist. And it fits into this webinar, I hope, because guess what? It turns out to be non-real. There is a natural logarithm of negative 1, and it appears to be pi I. Now, I've seen different models of calculators. This one I'm actually pleased. It's giving an exact result there. Often you get a decimal estimate of the pi, but you don't really see this. So that's pretty cool. All right, now I'm going to get even crazier. If I can take a logarithm of a negative number, can I take a logarithm of an imaginary number? Logarithm of I? Apparently I can. And I get an interesting result. I get 1/2 of pi I. Now, humor me for a minute. I don't claim to have the expertise to prove or to even assure you that all the traditional properties that we attribute to logarithms would hold in this new place where we've just gone. But if they did, then check out the screen to the right for a moment. We're going to agree I squared equals negative 1. And if it were appropriate to take the logarithm of both sides, we would have this statement. And if one of the properties of logarithms says this exponent could come out front, then this would say 2 times the logarithm of I would equal the logarithm of negative 1. Exactly true for these particular values, helping me be a little comfortable with this 1/2 pi I for this result. Well, okay, but where are they coming from? How, why in the world would the natural log of negative 1 be pi I? The best answer that I can come up for that is it has to do with the world of infinite series, where in fact E, and I'm going to use A specifically here as, again, as traditionally, imagine that's a real number, that this is the infinite series expansion for E to the A. But if you do substitute an imaginary number there, and I'm going to use BI to make the distinction, you get this math. E to the BI equals, and because some values of I, like I squared, become real, I cubed does not, I to the 4th does, you get a pattern here of every other term does not have I, and the others do. So I'm separating it into the two parts. And without a lot of explanation, because we don't have lots of time left, this is also a familiar series expansion for cosine, and this is for sine. And so we get this interesting result that e to the bi power equals cosine b plus I sine b. And I would say, well, let's put the particular value of pi for b. So e to the pi I should equal cosine of pi plus I sine of pi, which is negative 1 plus 0. Apparently e to the pi I should be negative 1. Let's check that on our calculator. E raised to the pi I is in fact negative 1. Now, I actually am sure of that result. I still have memories of my college advisor telling me this was the most beautiful equation there was, e to the pi I plus 1 equals 0, because it had the 5 most important numbers: the additive identity, the multiplicative identity, the basis of the natural exponents and logs, the basis of trig, the basis of complex numbers. And so he thought this was the most beautiful equation in the world. I've called it Euler's fabulous formula. And in fact, I own a book, and here's just an image of the cover that says Dr. Euler's fabulous formula. So there's an entire book talking about this whole thing about e to the pi I equals -1 or e to the pi I plus 1 equals 0. So if you'll buy into traditional properties, if e to the pi I equals -1, then it actually makes some sense that the logarithm of -1 could come out to pi I. Here's an interesting result. If you buy that and you raise both sides to the 1/2 power, then apparently e to the pi over 2I would equal I. Let's double check that by calculator. That seems to be holding again. And if you accept e to the pi over 2I as I, then this other example that we started with also would make some sense, the logarithm of I. So those are some connections that actually seem to make some sense out of both the logarithm of -1 as well as the logarithm of I. And not so subtly along the way there, we just raised the possibility of using a non-real number as an exponent. What about something raised to the I power? So if we go there, I'm going to go back to my calculator for a minute. I'm going to clear it off. So can we have, let's take E out of here. Can we have something like 2 to the I? Whoops. Pardon me because I didn't put the exponent there. Here we go. 2 raised to the I power. Well, it seems to exist. And it's another non-real complex number. And this over here on again on the right on my screen seems to help explain what that could be. Let's just see if this is really making sense. If this is 2 to the I, is this first decimal being shown here? Is it really the cosine of the natural logarithm of 2? No. And the reason is, luckily I see what the reason is. I have my calculator set in degree mode, which is not sensible for what we're doing right here. I'm sure glad that at least I realized what was up when, because those were supposed to match. It was supposed to be a effective demonstration. Let's change that real quick. All right, please pretend the last 1 minute did not occur. Okay, students, so if we use 2, we should have the cosine of the logarithm of 2. Let's see if that's a matching decimal. Why, look, it is. 0.7692 and so on matches. So we seem to have actually have a good interpretation of what it would mean to take something like 2 to the I power. Well, we're not going to go too much further. We only have about 5 minutes left, but I can't resist at least this one. If we agree that we can do things certainly like I squared, and we agree we can do things now like 2 to the I, could we do something even crazier like I raised to the I? Could, could that even have meaning? And just how weird would the answer come out? Let's see. Well, isn't that interesting? Not only does I to the I exist, apparently I raised to the I is a real number. Let's see if we can make some sense out of what just happened there. Remember this? That e to the pi over 2I was equal to I. We agreed on that a slide or two back. So if I make a substitution, I to the I should equal this quantity to the I. Multiply exponents, I get I squared or negative 1. I think I just figured out what this decimal is. According to this screen, this decimal should be e to the minus pi over 2 power. Let's check it out. Ta-da! Same decimal estimation. Not only is I to the I exist, I to the I is real, and in fact we figured out an exact form for what it really is. There's more to explore perhaps at another time, but just to give a little clue, if you start to go a little further and you raise numbers now, what if you took I to a, not just to the I power, but to something like this, 3 plus 4I. Notice that comes out imaginary. But if you take I to the 4 plus 6I, that one comes out real. And so what's happening is we're going to discover that you would get different results depending on actually the value that's in that exponent. And it's kind of a different world, I think, when we start to raise values like that. I think I'll close by saying, related to that, uh, taking things to the I power, um, we can take ith roots. Check this out. Can we take an ith root of 2? Sure you can. And I think the secret to that is to think of that as something like 2 to the 1 over I power. But don't forget the unique properties of I are that 1 over I can be rewritten as opposite I. So all of a sudden this value comes out the same as the reciprocal of 2 to the I. And we've already made sense of 2 to the I earlier. And we could use those properties to actually give exact expressions for that. And if we had more time, I would take you to one other interesting place. So I'm just gonna give a little tease about that. I'm gonna go back to a previous screen for a second, the one that looks like something like this. And if we kind of put a few of our ideas together about what the ith root would mean. Let me see if I have a better screen, because I apologize, that one is not. This is the screen I would rather. This was the result of what I was saying with if you took a to the 1 over I power and essentially took a reciprocal. This is correct. This helps explain. What are these values again? Cosine of log of 2. And but what if you think about some of the values that we put in here already? Like what if we put negative 1 in there? And we now agree that we have a logarithm of negative 1, which is I pi. And uh-oh, does that mean we can have something like cosine of I pi? In other words, can we take sine and cosine of non-real complex numbers? Here's a hint. The answer is yes. We're about out of time for tonight's webinar, so we're going to leave that as a, hey, if I can talk the powers that be into maybe doing some further explorations some other night down the road, maybe we can take a look at some more. But anyway, I hope the first 45 minutes was certainly things that you can apply in your classroom, in your curriculum. And I hope the last 15 minutes were at least informative and entertaining, and maybe even stretch some of us a little bit. I know a few years ago I was not familiar with some of these results and how they would happen. Before we quit, if there were any other questions left hanging or anything else we should tie up, Ish?
No, that was that last 15 minutes was mind blowing. I'm picking my jaw up right now just thinking of the possibilities. That's amazing.
Well, thanks. If you think back, you actually saw some of that once before.
Yes, at an MMC meeting.
At a, right, right. And so, as you know, I've done a portion of that, but there were some other thoughts. But anyway, I think that's the perfect place to stop for what we have this evening. Again, unless there's any other questions.
No, that was it.
So once again, thanks to all of you who joined us. If we have your email address, we'll be sending you a PDF document that summarizes what we've done tonight.